Hi, welcome back. Today we're going to talk about math. Yes, more math. Specifically, this is the continuation of our video on exponential functions and modeling them. So this is going to be the part where we talk about taking data and looking at it and deciding what type of function we would like to use to fit said data. So the two topics that we'll probably be looking at would be exponential and logistic. We know what they look like. Now we're gonna apply that to real life. So here we go. Things that you're going to need for this lesson would be a TI-84 graphing calculator. And if you don't have the calculator, Texas Instruments has been generous enough to extend their free trial of their software emulator that I'm going to be using on my computer today. So if you don't have that, you might want to pause the video, and I can put a link in the description below. So why don't you get that installed on your computer if you don't have a TI-84 calculator, and then we'll take it from there. Okay, so here we go. First problem, we have some data. This looks like census data. It says the table represents U.S. population between 1900 and 2011. It is 2020 now, so we'll see how accurate this information is. Use your graphing calculator to create a scatter plot and estimate an exponential growth equation using regression. Compare the results with the actual 2011 population. I think what could be also fun is we could go online and we could look up the population today and see if the model that we come up with will predict that. Okay, so here we go. So we're going to open our calculator, and that's our TI-84. So I'm using the TI-84 Plus here. All right, so if you use this, one nice way to, if say you've been using it on other stuff and you want to just clear everything, one nice way to start over is you hit the second button and see plus key here where there's the word mem above that for memory. So it's a plus and then 7 to reset, 1 all RAM, and then 2 full reset. So it just wipes out all your memory. Everything's good to go. All right, here we go. So how do we get this data that's in the chart over here? How do we get that into our graphing calculator? Right? Well, one way to do it, I'm sure there's other ways. The way I learned is you just go over to Stat, press and go to Edit, and you have all of these blank lists. List 1, List 2, yada, yada. So what we're going to do is we're going to enter all of these years into List 1 and all of the populations into List 2. So here we go. 1900. 1910. Just gonna prop this iPad up. Okay. 1910, 1920.
2 minutes later.
76. Beautiful. 10, 20, 30, 40, 50, 60, 70, 80, 90. Great. Okay. So now there's another thing that we could do. So we could go to our calculator here, and then we could go to second and then y equals, and I believe if we turn plots on, see that? Right now plot 1 is off. Notice how plot 1 has the option to plot L1 and L2. Let's do it. So we're going to turn it on. Yes. Scatter plot is what I would like to see. Beautiful. The x-axis would be list 1, the y-axis is list 2. That's exactly what we have. You could use these square markers. Let's do that because they'll really stand out because we're going to graph it through those points. And the color is blue. Wonderful. Enter, enter. All right, let's go to graph. Now I don't see anything there, right? Now if you notice the calculator is defaulting from -10 to 10 on the x-axis, -10 to 10 on the y-axis. But if we look at our data, we can actually adjust the window to actually fit our data. So press the window button. let's start our year, our x-axis. Let's start that at let's start at 1890. Even though they don't have data for that, we'll just buffer our graph a little bit. X max 1910. Oh, sorry. Let's make the X max 2030. 2030. Wonderful. So we're gonna look at all of those years from 1890 all the way to 2030. The Y min, the smallest population, and this is in millions, is 76. So let's make it 70. So the Y minimum would be 70, and the Y maximum, let's make it let's go 370. I don't know, 400. It's a nice round number. Great. Everything else looks good. I would leave all of the other delta X, trace step, leave all that stuff default. Now press graph. There you go. So you can take a look at that data. It almost looks linear from this perspective, actually. I bet you if we did a linear regression, we could probably get a line that decently fits that information. Now, a lot has to do with the way we scale these axes. We could definitely, change things a little bit. But it does look almost linear. It does not look exponential to me. So now, that's a scatter plot. We're just looking at the data. You hear me like hemming and hawing over like, oh, this kind of looks linear. It's supposed to be exponential. It is exponential. So you want to make an assessment for what you think the best function would be to fit that data so we can use it as a predictive model. So I'm going to come over to stat here. I'm going to say, all right, I would like to calc something. So I want to do an exponential regression on this one. So it's going to ask me what's my X list? That's L1. My Y list is L2. So we have that going on, which is nice. And they said, hey, would you like to store the regression equation? And thanks for asking, I would. So they want to store that in our Y equals setting, like Y1, Y2, Y3. So the way we would do that is there's a shortcut. Press alpha and trace. So alpha, and then press the trace button, and that's equivalent to what would be like F4. And now those are our Y vars, you would call them. So let's select Y1, and let's put it right there. And so it's going to take the equation that it comes up with to fit our data, and it's going to throw it right into our graphing calculator for us. So I think we're good to go here. You hit calculate. And so that's a generic exponential function. You see A is your coefficient, B is your base, and X is your exponent. And they're saying that the coefficient would be, that's scientific notation, 3.657 times 10 to the negative 9th power. So it's kind of a small coefficient. And the base is only 1.012. It barely qualifies as an exponential function. So yeah. And so you can look at it in context here. They've written that for us, very nice. And then we go to graph. And that did a pretty decent job hitting our data. So now, let's jump back over to this question. They're asking us, create and estimate an exponential growth equation. Cool. So let's write that equation down. I'm going to leave the one in the calculator for sure. But what they came up with is 3.657. So we have a population with respect to X equals 3.657156 times 10 to the negative 9th. I mean, we could like literally, move the decimal over if we wanted to, but this is fine. All right, so times 1.01261 to the X power. Okay, so I should be able to plug in any year now and get some results. So they say, okay, create a scatter plot and exponential growth equation using regression. We did that. Compare the result with the actual 2011 population. So there's a couple ways you can go about this. One would be to go into the graph again, and then you could go to second trace, and we could evaluate things that are actually literally featured on that graph. So I could go value, and it's going to ask me to plug in an X value. So we would plug in 2011, and it's going to give us the corresponding Y value that goes with that, which is 326.9. Okay, so that's cool. It's definitely not exactly what's on that graph, right? It's off by a little bit. That being said, we're going with an exponential model, so it's assuming that it would go up there. It's not going to be perfect. Again, it's going to try its best to fit those points that we gave it. So yeah, we could plug in other years. Now I'm going to show you another trick. I think that is even more fun, because we would rather go like P of 2011 or P of maybe even 2020, right? Rather than going back to the graph and going to value, you can go to the home screen, hit second, and then mode. That takes you to this home screen. And if you recall, the Y-vars, they live at alpha trace, and I can select Y1. I can actually treat Y1 as a function in function notation. I'm just going to put up some parentheses here. X, and I'm going to plug in 2011, like we just did. So Y1 of 2011 equals 326.9 million. So 326.9 people. Okay. Curious. Let's check out 2020. So we're going to go alpha trace Y1 of 2020. So how accurate was this predictive model? So they're saying that the U.S. population would be 365.96 million.
A few moments later.
So they say it's 328.2 million. Yeah, so it seems like this predictive model is not 100% accurate. Granted, this is taken from a math textbook, so I mean, I'm assuming their source is valid. It's possible that there are a myriad of factors why the population would have not grown as quickly as... Oh, actually, this is 2019. They don't have the 2020. I mean, we're in 2020, right? That would make sense. Still, though, 2019. Hey, you know what? Let's jump over to 2019. Let's just see what that turns out to be. So alpha trace Y1... 361, and they're saying it's 328. So yeah, I mean, if you look at this growth model that they have, this looks sort of linear again, but it looks that way because of the scale of the axes. You have to keep that in mind. We're talking like that y-axis is not only like spanning, like, you know, going from 100 to 300, that's going from 100 to 300 or 100 to 400 million crammed in that, you know, in that space. So yeah, it's easy to see that as being as linear. So okay, moving on. So the main takeaway from this is you learned how to make a list, and you learned how to do a scatter plot, and also to create a regression function. Okay. One thing about stat plots, sometimes they just linger and you forget. So you can either reset the calculator when you go to use it for something else, or just come up here and then turn your stat plots off just by selecting that plot, and then you should be good. Okay. So you don't see the plots anymore. And I'm going to just go ahead and go second plus 7, 1, 2, and I'm just erasing all that stuff that's on my calculator. Okay. There is another example here. So for those of you who feel like you really know what you're doing, I would pause the video and take a look at this. Here, I'm just going to add another page. I always forget to do that. Okay. There we go. So yeah, pause the video. See if you can enter this in your calculator, come up with the requested regression lines, and we'll check back in a sec. I'm gonna probably edit out all of my work. You can watch me. I'll go fast on the calculator. If you're still struggling, you can watch me go through the steps. Okay, so here we go. Example 2 and our last example for this video. All right, so it says table represents a population of the state of Florida and Pennsylvania between the years 1900 and 2010. Okay, this is the state of Florida and Pennsylvania. It says using your graphing calculator to create use your graphing calculator to create a scatterplot and estimate the exponential growth equation using regression for the states of Florida and Pennsylvania. So exponential is unrestricted, but for many populations, the growth slows down when it approaches maximum sustainable population. So what they want us to do then is use the calculator to estimate a logistic function to determine the maximum sustainable population. So first we're going to go exponential, and then we're going to see if it would fit better with a logistic regression. That's basically the moral of the story. So why don't you try to do that on your own? But the big takeaway is you're going to have 3 lists. L1 should be shared. That's going to be the domain for both functions. It's going to be all the years that are common to both Florida and Pennsylvania. L2 could be Florida's population, and L3 could be Pennsylvania's population. Just be sure to remember that when you're generating your regressions, okay? So let's do this. Stat, edit, L1, and I'm going other deletion, 1900. Okay, so we have the data here. So let's make let's make some plots, right? We're gonna go y equals. So let's turn on plots 1. We're gonna do 2 different plots. We're gonna do plot 1. Turn that on. So this will be the population of Florida, and we're good to go. We have everything there: L1, L2, and we're in blue. Great. Second, and then let's turn on plots 2 on, and we're going to leave X list as L1 because that's common. This can be L. All right. So we're going to go alpha L, and oh, I see it. Nope, clear. It's I think it's here, second and then 3, L3. Ha, whew. Nice save. Okay, and then that's going to be in red. Cool. Maybe we should change the markings. We'll make the little solid ones. All right, cool. And then of course we need to change the window to go from, let's go 1890 again, to we'll go to 2020. That's our year axis, right? Our time axis. And then a population. Yeah, it looks like we start close to 0 in Florida. That's weird. Or 500,000. What? Okay. 0, and then hit me with 25. This is in millions. And let's look at that graph. Wow. Okay, so the blue one, right? That's our first one. That's all right. That is the first one, I believe. So blue is Florida, and then red is Pennsylvania. So Florida, yeah. I mean, it's really. I thought that would look like it was taking off more, and it's not. So. Interesting. And then the Pennsylvania one, seems to spike up there. So anyway, all right, so just for fun, let's come in here and let's do some regressions. So first one we're going to do an exponential on both. So we're going to do exponential regression, L1, L2, and I'd like to store that equation in alpha trace y1. Okay. And then we're going to do it again, stat, edit, exponential. And we're going to go L1, and then this time we're going to go second L3, and we're going to store that in alpha y2 trace. So we're going to put that in the second function slot, calculate, lovely, and let's take a look at that graph. So the blue one takes off. Now notice how the the Florida graph, it just, it's uninhibited and it just keeps going up and up and up and up and up, right? But if you look at the data, it almost looks like it's wanting to make a little bit of a turn there, right? So it's worth noting. We'll just write down our answers here. So the for Florida, we have the population is equal to 2.04196 times 10 to the negative 29th. And then the A coefficient is, the B coefficient, the base, 1.0350396 to the X. I know you don't need all that information because we have it stored in the calculator. And then Pennsylvania is going to be, we'll call that, we'll just call it G of X, even though G doesn't mean population, 2.08569 times 1.005537 to the X. All right. So those are our two exponential growth functions that could potentially do a decent job. So as it mentions here, exponential is unrestricted, but for many populations, the growth slows down when it approaches a maximum sustainable population. Yeah, I mean, I guess maybe people will start leaving the state if it's too crowded or something. I don't know, maybe the schools are too crowded. I don't know if we're running out of food yet, but yeah. So, but yeah, I guess it's possible that the population might start to slow. But and that will happen eventually in the world anyhow. I mean, there are finite resources, so populations will eventually slow down. So anyway, so let's take a look now at one more thing. I know we've been at this for a while. Let's do a logistic regression, okay? So it's funny how I spaced it out like that. I should slide that other part up. So it says use your calculator estimate a logistic function. So let's look at both of these. We'll go y3 and y4. So y3 will correspond to y1. We'll look at Florida first. So let's go stat, calc, and we're going to go logistic. It's going to go L1 and then second L2. And where should we store it? Y3. Great. It's thinking. Okay, and that should look familiar to you. So the way they're writing this is it's for Florida again. If you don't mind, I'm going to just go right here and write the logistic version. So it's going to be the population with respect to X as a logistic growth would be, and then times E to the negative B. So it's negative 0.04803, and then x, times x. Okay, power. And let's take a look at it. Okay, and we're going to look for one more. I forget what color. I guess I left it. That one's black. Look at that. It actually hits that last point too. So I'm thinking that might be a slightly better model. And you can see that our carrying capacity would be up here. They're saying that the maximum population is approximately 27 million people. And then lastly, would you try to do this on your own, but let's just also just do the logistic function for the other second for Pennsylvania. And we're going to store that in Y4. Thinking. All right, there it is. I could write this all down for you. There it is. You see it. You can just insert all of these coefficients into their appropriate spots, and then we can you can see that all the graphs are in place. Looks like the carrying capacity, which would go here, this about 12.8 million, and then let's look at that graph. So those are our first two exponential functions, and then I think we see that logistic is much more appropriate in this particular context. Actually, let's jump over and turn the first two off, and I think I could just do that by hitting these equal signs. Just highlight the equal sign and hit enter, so that should turn that graph off, and then we can just look at only the logistic now, and much more accurate. So anyway, in summary, we learned how to use our calculator to input data and run regressions on said data in order to find an equation that models that data so that we could use it as a predictive model. So it does seem that in this second context, the logistic growth would be more accurate. And I would even encourage you to maybe look at the U.S. population, and why don't you run a logistic regression on that data? You probably already deleted it, but try it. You still have that x-axis in there. Just go and change the population and do a logistic regression, because I wouldn't be surprised if that's more accurate. Anyway, take care. Be well.